are like this. Electrons as dots is a drastic oversimplification. Heck yeah. After we just got done talking about all these complex shapes and stuff, and now we're just making dots, right? So as we make these dot structures, we do have to understand there's a little more going on. So the electrons are not always shared equally, okay? So here I think of when I used to, go on vacation and have to share a double bed with my sister. You know where this is going, don't you? It's the blankets. Because one person always takes the blankets. I have no idea. I actually have no recollection of who it was. Suggests it might have been me, and I blocked it out. But you know how that happens. So, yeah, we're sharing the bed, but not sharing it equally, right? So when electrons are shared, they are often not shared equally. And a bond like that is called a polar covalent bond. So here we have an illustration showing hydrogen and fluorine. So when hydrogen and fluorine share a pair of electrons, fluorine is hogging the blankets, hogging the electrons. The electrons are spending more time over here and less time around the hydrogen. So as a result of that, one end of this molecule is going to be a little bit positive. So this one, that's the negative. This side's going to be a little bit negative, and this side's going to be a little bit positive. That's a lowercase Greek delta, which kind of looks like a English, or whatever they call it, regular D with a posture issue. So this end is a little bit negative, and that end's a little bit positive. So here we have our HF molecules just floating around, and they're going to be randomly oriented. If we turn on an electric field and make this plate negatively charged and that plate positively charged, all of these guys are going to snap to attention and point their positive ends towards the negative plate and their negative ends towards the positive plate. And you can get them to all line up like that. They're polar. One end is different than the other. So the word polar, you can think about the north and the south pole of the planet, right? They're different ends. And that's a magnetic field. One end is different than the other. A polar covalent bond has one end of the bond that is different electrically, right? So here we are sharing, but we're sharing unequally. So these bonds are kind of between an ionic bond, where they're not sharing. One atom took the electron from the other, or, framing it more positively, one atom gave the electron to the other. And at the other end, we have the covalent bond, where they're sharing perfectly equally, right? So this is kind of in between. Well, who is hogging the electrons? The scale for that is called electronegativity. It can be defined as the ability of an atom to attract electrons to itself in a chemical bond. And it turns out, in general, it's inversely related to atomic size. So this is a chart that gives us the electronegativities of most of the elements. We're not actually going to use those numbers very much. There might be a homework question or two. What I do want you to remember is that fluorine is king of the mountain, right? Fluorine up here, fluorine has the highest electronegativity, is the most attractive to electrons. So when fluorine shares with other atoms, it's almost always an unequal sharing, a polar bond. And so this is going to follow the same trends that we learned in the previous chapter. Personally, the way I remember electronegativity is fluorine is the top dog, and so whoever's closest to fluorine in general is a higher electronegativity. Notice who's missing here, who got cut off on the end there. Noble gases. The noble gases form almost no bonds. So why put them in here? They just left them off, okay? So we should be able to do something like this, arrange these elements in order of decreasing electronegativity. So we've got phosphorus, sodium, nitrogen, and aluminum. And the way to approach that problem is first to find them on the periodic table. So here we have phosphorus and sodium and nitrogen and aluminum. So in order of decreasing electronegativity, that means the ones with the smallest electronegativity is last, the highest electronegativity is first. Which of these elements is closest to fluorine on the periodic table? The nitrogen. It's pretty close there between nitrogen and phosphorus, but it definitely is the nitrogen. So nitrogen is the most electronegative of these guys. And who is the furthest away? Sodium. So sodium's the lowest. And then real close to nitrogen is phosphorus, and the next furthest away would be aluminum. So this is, predicting relative things, just like we did with ionic radius and first ionization energy, metallic character.
Oh, so is this highest to lowest?
This is going highest to lowest because this is decreasing electronegativity. And I really try to emphasize these questions because I do put questions like this on the exam. And sometimes students misunderstand the question and they give me the exact opposite answer. So I don't want that to happen to anybody. Here, the greater than sign is also a clue. So there's greater than and less than, and those can be confusing. But this end is big, and this end, the pointy end, is small. So the pointy end is pointing towards the thing that's smaller, and the big end is on the side of the thing that's larger. So here, N is greater than phosphorus in electronegativity. Any questions? Well, so we've got ionic bonds, we've got covalent bonds, which could be called pure covalent, or I prefer to call them nonpolar covalent bonds, and then we've got these polar covalent bonds in between. And it's not just that there's three distinct categories. This is not a quantum situation where you're one of the three. There's a continuum here. And so the degree of bond polarity will depend on the difference in electronegativity between the two elements. And so somewhat arbitrarily, we've decided that if the difference is between 0 and 0.4, those are considered a nonpolar bond. They're close enough, nonpolar bond. If the difference is 2 or more, we consider that an ionic bond. And if it's somewhere in between 0.4 to 2, then we say it's a polar covalent bond. But again, I said that we weren't going to really use those numbers, and so the 0.4 and the 2.0 is not something that you need to remember. Where do I write that? I think I write it right here. Whoops. If you have the same elements, oxygen and oxygen, chlorine and chlorine, what's the electronegativity difference? They're equal. So that's going to be a nonpolar bond, right? So if it's the same two elements, then it's a nonpolar bond. That just kind of makes sense. What if we have a metal and a nonmetal? Oops, metal. Metal and nonmetal. We learned earlier that those make ionic compounds, right? So if you're looking at the bond between a metal and a nonmetal, I want you to tell me that it's ionic. What if we have two different nonmetals? There are exceptions, but most of the time they're going to be polar covalent. There's one exception, just one, that I want you to remember. One exception: carbon-hydrogen bonds are nonpolar. If you can remember that, that's good enough for most everything. And it's very useful when you get into OChem. That's why I make that exception for the carbon-hydrogen bond, because that'll be really important in OChem.
Just when those two are paired with each other, not with anything else?
If it's carbon and hydrogen, tell me it's nonpolar. If it's two of the same element, it's not polar. Because obviously, they have the same electronegativity, so the difference is zero. If it's a metal and a nonmetal, we learned earlier, that's an ionic bond. And then what's kind of left in the middle is what if you have two different nonmetals other than carbon and hydrogen? Most of the time, it will be a polar covalent bond. So let's go back and look at this table here. Oops. So here's carbon, 2.5. Here's hydrogen, 2.1. So the difference there is 0.4, which is right on the edge of nonpolar and polar, but it's considered nonpolar. There's some other elements in here, carbon and sulfur, carbon and selenium. There's some other combinations in here where you could get a nonpolar bond between two nonmetals. But those don't come up very often, and they don't come up in Chem 1A where they're important at all. So that's what we're going to do. Another way to measure bond polarity instead of looking at the difference in electronegativities is by measuring the dipole moment. So there's a dipole moment anytime you have a separation of positive and negative charge. And so that's equal to the charge difference, the magnitude of the charge, and the distance between them. So the closer they are, the larger the dipole moment. The higher the charge, the larger the dipole moment. And a common unit for that is the debye. And this whole business here, I want you to know what a dipole moment is. It's when there's a difference between a separation of electrical charges. But we're not actually going to calculate that or do anything with debye's. We could also look at percent ionic character. So looking at the bond's actual dipole moment compared to the dipole moment it would have if the electron was transferred. And we can graph percent ionic character versus difference in electronegativity. And what we see here is there's two clusters of bonds here. And no bonds are actually 100% ionic. So we talk about, the sodium gives its electron to chlorine, and then they're just attracted because of their positive charges. Well, it's kind of like a exaggeration, right? They don't actually totally give it. There's some strings attached, right? But it's just easier to think of it that way, and most of the time we can. But what we see here is all of these guys, except for HF, anything over 50% is considered ionic. Well, what kind of elements do we have in all of those guys? Metal, nonmetal, right? Metal, nonmetal is going to be an ionic bond. Some are more ionic than others. Here we have HF. That is the most polar bond between two nonmetals, but it's not quite ionic, and then these guys are all down here under 25%, because their electronegativity differences are much smaller.